Okay, thank you. I've started. Okay, so today we will be continuing our discussion on supervised learning, and so we'll do logistic regression today, and, and then show you how to estimate parameters using different kinds of optimization techniques. And these optimization, so today's lecture is going to be more or less the foundations of deep learning. Okay, so you probably may want to focus more attention to this. So logistic regression followed by the optimization techniques that we're going to talk about is more or less the foundations of deep learning. Okay, feel free to stop me, ask any question whenever you have any doubt or anything. Okay, so just quick recap of what we had been doing last time, like to bridge the gap in case you have any. So we have been talking about logistic regression. So it is inherently a two-class classifier. So the class levels could be 0, 1, positive, negative, or any kinds of like two number of classes too. So in that situation, we will be doing with this logistic regression classification. Okay. And what we do that given a feature vector with the features which I denote by x, the probability that it will belong to class 1. Okay, so that is the kind of the thing that we're going to do here. Okay, so it's a probabilistic classifier using this feature vector that we have, and we will see how we can do this. Okay, estimate the model parameters and so on. So the assumption that I talked about this one, I'm just running through this quickly because I've covered this one, so that the linear combination of the features is the log odds of this, and then you equate this, then you're going to get e to the power z by 1 plus e to the power z, where z is the linear combination of features with the appropriate weights, theta 0 up to theta n, and theta 0 up to theta n are called the model parameters, so which we need to estimate. And x1 up to x10 is known to you, which is the feature vector. Okay. And so we talked about this also, that this particular expression can separate the linear decision boundaries because the function z here is basically linear combination of features. So we'll try to figure out the straight line, a good straight line which will separate two different classes, class 0 to class 1 and so on and so forth. Okay. And we also look at the different numbers, and so we can also extend this for non-linear decision boundary when the boundary which separates two classes is not linear. It could be of any kind of curve, okay, and so on and so forth. So given that this is a quadratic curve, quadratic equation, so what we could do, we can actually change the z from linear to quadratic, okay. So you are going to get this kind of thing which we talked about. And so that is the thing basically up to this point we talked about in the yesterday's last lecture. So today we are going to start from here and take it forward. So in general, so main thing is basically how you play with z. Okay, so expression z. And so in general, we can do some kind of generalized solution, which is additive models. I give you a couple of examples in the next slide. But in general, what you can do, instead of taking linear function, quadratic function, this like that, and so on and so forth, prediction we can do based on a linear combination of basis functions, a set of basis functions. So a basis function is nothing but, as you know from basis vector, a function, some set of functions, and if you linearly combine these functions, you are going to get all possible function of different kind. Okay, so that is the kind of the basis functions. So here, for example, the basis functions are phi1x, phi2x up to phi mx, which is basically taking input data in d-dimension, real number, so vector space, d-dimensional data it is taking, and of course this is giving one scalar value. So it's a multi-dimensional data it is taking of d-dimension and giving you a scalar value. So therefore, if you have the basis functions, if you kind of know the basis functions, phi1x, phi2x, and so on, so you can actually compute z by taking linear combination of all these basis functions. So I have a couple of examples in the next slide so that you understand it better. So here is an example, say, okay. So this is the definition of basis functions and everything. Okay, so now examples could be, for example, I can take phi ix equals to x to the power I, where I could be 1 to m. Okay. Now, if you do that, for example, you can see that z is going to be a polynomial of a degree m. Okay. So simply by setting this basis function to x to the power I, you can generate polynomial of degree m. And depending upon the value of theta 0, theta 1 up to theta m, you can have different kinds of polynomials. Okay. Similarly, if I set theta I is equals to x, then you are going to have the plane, the hyperplane. So theta 0 plus theta 1x up to theta dx. So which is basically hyperplane. And by playing with the different kinds of these values of theta 0 up to theta d, you can have different kinds of hyperplane. Okay, so from left to right, right to left, whatever. Okay?
Excuse me, sir.
Yeah, please go ahead.
Sir, like I don't understand. What is theta 1 x? Like, isn't theta 1 some number?
Theta 1, yes, these are basically scalar values. Theta 0, theta.
So isn't it equivalent to theta 1 plus theta d of x? Why are we having different parameters?
Say again.
Sir, isn't it z equal to theta plus theta 1 plus dot 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 till theta d of x? Why are we having, like, the basis isn't unique, right?
No, I'm not understanding which part you are referring to.
So should it
in
be
the second?
xi? Should it be xi in the second part?
Yeah, like
Should it be
xi. You just
Because
put x.
applying multiple parameters.
yeah, right. Yeah, you are right. You are right, yes. So it has to be indexed, yeah. Right. Sorry, yes, so, right. Thanks for the pointing this out. Okay.
Sir, sir, one question. Sir, here x is a d-dimensional vector, right? So in the examples, you have taken only numbers or vectors?
So here basically I have taken like numbers. Yeah, I consider only numbers, but you can extend this to the dimensional space. Okay. Yeah. Okay. Yeah. Now the biggest issue is now basically playing with this theta and this, whether you want to get linear or you want to get non-linear, quadratic, higher dimensional polynomial and things like that. All you can do. That is not something is very complicated part. Okay. But you know, all models I mentioned that all machine learning models will have set of parameters, the thetas, theta 0, theta 1, theta n, whatever. Okay. So you fix the functional form, but you do not know yet the values of all these thetas, theta 0, theta 1. And that is the case for all machine learning models, be it support vector machine, be it neural network, be it logistic regression, and whatever. All for all parametric models, you need to deal with that. So one of the most important question that basically how I get all these values of these parameters. Okay, and that is where playing with optimization functions and then the objective function optimization techniques and everything will come into picture. Okay, and often substantial amount of effort goes into finding out those parameters. Okay, now how do we estimate the model parameters? Okay, what's the approach that we can basically take, we can follow? Okay, now take for example one sample from the training data. Okay, and if you do that, then let's say x be the input sample or the feature vector. Take one sample, so x is corresponding feature vector, and y be its class level, because you are dealing with supervised learning, so you have both x and y available to you, and y is the class level. Okay. Now, given the input sample x and the model parameters theta, what is the probability that x belongs to class 1? And that is precisely the question and the objective of logistic regression. Okay. So with respect to the model parameters theta and given the feature vector x, what is the probability that the x will belong to class 1 with some values of theta? Okay. So we know it from logistic regression that this is something like this. I basically use shorthand for that. LRX, I will basically by LRX I will call the whole line. Okay, just shorthand I'm using. Okay. Now, what is the probability that X belongs to class 0? The other class, you have two class classifier. So if it is LR X, then it is going to be 1 minus LR of X. Because there is only two class, so you know the probability of the other class. Okay? Well, that's the basic things. Now, what we do? Now, if I put together these two expressions, okay, what I can get is something like this. Now, probability that the label would be y given x comma theta, theta is the model parameters, is something like this, that LR x to the power y into 1 minus LR x to the power 1 minus y. Now, if you follow my steps, that from previous two lines, I had y equals to 1 or 0. Okay, so two expressions, but I'm putting them together into generic form simply using y only, and then just reorganizing my expression to put these two equations into a single equation. Okay. So any doubt on this? Anybody has any question? Because so this expression you are going to use in the next slide for optimization. Yes, please go ahead.
So LR stands for?
LR stands for so if you look at this expression before, so LR stands for this one, the probability of y is equals to 1 given x comma theta. Okay. So okay, that's the LRX. Which is called logistic regression of x, something like that. You can basically linguistically interpret it. Okay.
Yes, sir.
All right. Okay. So anybody has any doubt up to this? All right. Okay. Yeah. Any question?
The expression, sir, the expression is like if y is 1, it will become LR of x, and if y is 0, it will become 1 minus LR of x.
Right.
So you are merging it, right?
Absolutely. Yes.
Is there any other meaning for this?
So the meaning is basically okay. This is objective, of course. The objective is to that I'm going to use this expression to form my objective function. Next slide, I will show how.
Sir, can you please explain this expression again? That why did we write this equation?
Okay, so you have this one, right? You can follow my mouse pointer. Can you follow my mouse pointer?
No, sir.
Not yet. Okay, let me just then basically use my pen to illustrate the whole point. Okay, all right. So let's say now, if you look at this, can you follow these lines that I'm drawing on this?
Yes, sir. Yes, sir.
All right. So this one expression, okay, and this another expression. Two expressions. Now I am simply putting this together to expression into a single expression. This. Now here, my expression, the two equation boils down to one equation where I no longer have y equals to 1 or y equals 0. I simply expressing this whole things in terms of y only. So depending upon the value of y, the expression on the right hand side will determine whether this will be this or this will be this. The first one or the second one. Make sense?
Yes, sir.
Okay. Now why I want to do this? You have rightly asked this question. The reason that I want to do these things, I want to use this simplified expression to compute or to figure out my objective function, which I will want to optimize to get my model parameters. Next slide, I'm going to show that. Okay?
Yes, sir.
All right.
So,
yeah, please.
So we are basically like maximizing it to an extent. Like
we have to maximize it because this is a probabilistic classifier. We have to maximize it. Yes, that's true. But
so,
you know,
so in an ideal case, it would just be 1. It will be equal to 1 because all the probabilities will be equal to 1.
But you know that depends on the x. If x belongs to class 1, then you of course you want to maximize the probability and you want to get it to 1. But if it belongs to class 0, then of course you don't want that. You want to have it close to 0. Okay, so it's conditioned on x, what x you have here. Okay, because you do not know yet what would be the good values of theta. So theta and x combinedly will determine that what would be its best probable class level. Okay, because you do not know yet theta, and theta you have to figure out.
Okay, sir.
Okay, all right. So let's see what we do in the next slide. Okay. So yeah, so this is my kind of the expression that I am dealing with. Okay, all right. Now I have to come up with a likelihood function. Okay, so people call it likelihood function when you're dealing with probabilistic things. Sometimes you deal with like error functions, profit function, loss function, all kinds of stuff people say, depending upon what you want to do. So because here we basically want to estimate these probabilities, okay, so it is called the likelihood function, nothing else. So what the likelihood function will look like? Now we have n number of training examples. So you have a training level data where of n training examples, and we have the feature vector and the corresponding class levels of all of these examples are known. That's the setup that I have. Okay, now, so what I like to do from these n training examples, I would like to construct one composite likelihood function. So likelihood function means the objective function. Okay, that's the function that we will have to basically optimize. So I simply use shorthand notations here. So L of capital theta is equals to probability of class of y, so capital Y given capital X, and where the capital Y is basically all the class levels that I have. Okay, up y2 up to yn, class levels for individual points, and the X, capital X, I denote by like the features of the corresponding input data. This is a shorthand notation. Okay, just to express things more compactly. That is it. But in next step we will show how we can work out with this. Okay. So next what we do, we basically now they assume that the training examples are independent. Okay, that means the x, y, y is independent of x2, y2, independent of x3, y3, and so on and so forth. Okay, there are n examples and they are all independent. And this independence assumption is something that we make all the time in machine learning and statistical learning. Okay, otherwise that things will become intractable, computationally very difficult to deal with. Okay, so it simplifies the computation, no other purpose. It's probably not the best realistic assumption that we can make about the data, but we have nothing to do except because we cannot manage the whole thing, so simplify the whole thing and make independence. Okay, and that we do IID assumptions and all these things we do. Okay, all right. So if we assume that the examples are independent, okay, then how my likelihood function will change into? Okay, so here now that my examples are independent, so it's just like the joint probability will will get converted into the individual probabilities product, right? That's the independent assumption. Product of this into this into this into this, and so on and so forth. So for every sample, you have the individual probabilities and this will take multiplication of that. Okay. Okay, all right. So this is my kind of my initial likelihood function. Okay, I do not know yet thetas. I know all the yi's, xi's, but I do not know yet thetas. That I have to figure out. Okay, so I am basically in the process of figuring that out. How I should figure out theta, good theta. Okay, all right. Now go back to my the expression from my previous slide there, where I basically use this expression, the compact expression that we have been talking about. So we can use that to kind of replace this thing with this thing. Okay, so I know that this expression I have, I can replace this one, I'm going to get this one. Okay, so this is my likelihood function. Okay, and I have to basically optimize this likelihood function. But optimize means with respect to what? With respect to thetas, because thetas are the parameters in this particular expression. So I have to optimize this with respect to thetas. Okay. All right. Now what we have, I mean, what I can do now? How we can optimize this one? Now, and somebody was pointing out that we have to maximize the likelihood because this is a likelihood function. Okay, you have to basically measure the likelihood or probability of class 1 or class 0. So you have to maximize this one. So we have to maximize this function. Okay. But as you can see from this that.
Excuse me, sir.
Yeah, please.
Sir, I'm not understanding why to maximize this function.
Okay, so if you go back to your expression of LRX, what's the definition of LRX? LRX is basically that probability that a particular sample will belong to class 1. Given the x, what is the probability that it will belong to class 1? Okay, and 1 minus LRX is basically it will belong to class 0. Okay, so what do you want to do? For those examples which are belonging to class 1, you want to maximize that probability so that they belong to class 1. It's a probabilistic classifier. And the examples which are not part of class 1, you want to basically maximize that probability to class 0. Okay? So that is why basically you have to maximize this whole probability of all the examples.
Yes, sir. Got it.
Next slide.
Hello, sir.
Yeah.
So does the expression give the probability of entire set being correctly classified?
Exactly. That's right. That's right. Exactly. That is precisely the goal. Okay? Yeah, you're right. Okay, so okay, all right. So now that L theta is complex to manage, and again we always play this mathematical trick in mathematics. When you cannot deal with one expression, then you have to tweak a little bit here and there and so on and so forth to deal with that. Okay, so here is the standard thing is called the log likelihood. So because the L theta and log L theta, so if L theta is maximum for some value, log L theta will be maximum also. Okay, so because there's monotonically increasing function. So I simply want to maximize log of L theta because log of L theta will simplify my expression. So from product to you can get the sum over the expressions. Okay. So I will be dealing with this log of L theta with respect to all these model parameters that you have. So this is more or less the trend for most of the machine learning, like supervised machine learning problems, where you have the parametric models. Okay? More or less this is the trend. You figure out the objective function and then you try to optimize using some optimization techniques. Okay? We have not talked about the optimization techniques. We will see later on in a few minutes. Okay? So this is the expression that I have, and I now have to basically optimize this likelihood function with respect to model parameters and so on. All right. So what do you do? Now, in order to do that, I want to apply a thing called a strategy called or an algorithm called stochastic gradient ascent. There is a thing called stochastic gradient descent, and here we have to apply stochastic gradient ascent. So descent will be used, as you know from the name, then when you have to minimize something, you're descending, okay, from top to bottom place. And here we are maximizing things. As a result, you have to apply stochastic gradient ascent. So you have to maximizing things. Okay. So gradient ascent rule, you can basically see. I'm just writing down. I've written down this rule here, but a couple of slides later, I will show you how this actually came into first place. So here, this is the gradient ascent rule. So say you have basically want to estimate a particular value of a particular parameter. So this is the new value. This is the old value you had. This R is it's called learning rate, and this is the derivative of this expression, objective function with respect to particular theta. So essentially, what you use, so this is the gradient, okay, the derivative. This one, and R is basically learning rate.
Hello, sir.
Yes, please.
I have a question in the part before this.
Yeah.
We just defined L of theta, some particular function. I just want to ask, how convinced are we that this particular the theta that we generate using this particular function will be fit to the newly generated data, which is not the training set?
How confident we are
about the acceptance of these parameters theta for the newly generated set of data, which is not the part of training set.
Part of the training set. Yeah, that's a good question. Okay, all right. So let me try to answer this question. Okay, so let me first tell you the difficulty and then probably a reasonable solution. So difficulty is that you never know the nature of the data that you are going to see in future. That means the test data. Okay. So typically when we do machine learning things then in a kind of normal setup, we have the data, we split the data into train test and then run these things and test on test sample. But in real setup, you never know the nature of the data that you're going to encounter in future, right? We never know that. Okay, that's the limitation. So you probably cannot address the problem wholly, in a foolproof manner. But what you can do then? The question is what you can do then. So one of the well-known solution to this is that you apply cross-validation approach. So in cross-validation, what you do, say you have a data set And then basically you create multiple folds of the data set. You randomly partition the data into say k sets. Okay. And then what you do, you use k minus 1 set for training and the kth set for testing. And then you rotate this for all sets. So if there are k folds or k partition in your data, in your training data, then you train your algorithm k times and measure the performance on each and every fold as a test case. Okay, and adjust your parameter in such a way that you basically get high accuracy on all the folds, but at the same time you have low variance across the folds. Okay, so that is the kind of strategy that we use. Okay, any follow-up question on this?
Okay, sir. It's not quite clear, but I guess it will get clear as.
Yeah, so you get to know how things are done, but this is not a foolproof approach. Nobody knows how to deal with that situation. You never know that, because if the data is not part of your training set, at least some part of it, then difficult to kind of figure out a model which will work well. Okay. Okay. So what I do here then is basically the gradient ascent we want to apply, because we want to maximize these things. And we basically need to compute the bunch of parameters. So here we are using the partial derivative, because this is a kind of multivariate expression that we are dealing with. So you have to do partial derivative and so on and so forth. So from likelihood function, you can compute the partial derivative of this likelihood function with respect to all the parameters, and then you get this expression. So the expression that I worked out, but you can basically, this is a very simple expression. You can work it out.
So you are not updating theta j with theta j new. So how can we change the value theta?
Theta j. So here is this iterative definition. If you look at this line here, so in this particular line, so theta j new is equals to theta j old plus r into this. Okay. That's the
yes, sir, but you are not updating theta j old with theta j new.
Well, I mean, if you really like to have that kind of expression, so something like this. So you can basically do this kind of thing, theta j. So this is I plus 1 is equals to theta I j plus r into del L del theta j. Okay, so does this satisfy you? If I do that, where I is the value from the ith iteration.
Yes, sir.
Okay, so yeah, I use the shorter notation. So old and new means this current value and the new value and so on. So, but yeah, okay, this is probably the most appropriate form. Okay, so you do this for all the parameters in this model. We are going to look into these things in great detail later on. So a couple of slides from now. Okay. And so basically then you compute the partial derivatives of the log likelihood function with respect to the parameters, and then going to update the values and so on and so forth. Okay. So this is more or less this kind of the things that we basically do, but the heart of everything in this particular case is that the optimization function that you're going to use. Okay, that optimization technique, because once you have the likelihood function or the error function or the objective function, then basically you have to optimize it. Okay, so that you have very good performance predictions on the training set. That's what you want to do. Okay. All right.
Sir, here we are taking only one training example at a time, because the summation is not there.
Yeah. So So in stochastic gradient descent, you take, or gradient ascent, you take one training example at a time. But you can extend this to, for example, all the set. You can also take the subset of that sample. So there are many variations, which I will be describing in a moment. Okay.
And sir, how can we guarantee that this gradient ascent is actually giving us a better theta?
Well, I think okay. So while you are updating these parameters, at the same time you are computing the prediction accuracies as well. Okay. The moment you update some values, you can, for the samples, you can predict what your model is telling about their levels. So the predicted levels, if the predicted levels match well with the actual levels in your data, then you can say your model is learning very well. Okay.
Okay.
because you already have the actual level in the data, so you can simply evaluate that.
Newton's method applied in many dimensions together.
Sorry?
Isn't this Newton-Raphson method applied in many dimensions together?
So it's a not Newton-Raphson method, but it's like not
Close to
exactly.
it, right?
So Newton-Raphson method, you also have the second order derivative, but you do not have that here. You only have the first derivative. Okay.
Okay, sir.
All right. Okay. So because you are going to see in a moment that these most of the machine learning functions that we deal with is highly non-convex. That means there could be many local minima and things like that. So like finding out the good values of theta using other techniques, not really helpful. So the gradient descent or gradient descent something is known to be very well performing in this setup. Okay. All right.
So what is learning rate?
Okay, yeah, that's a good question. So you will see in a moment, but learning rate is something that's kind of, you think about jump. Okay, that jump, how much jump you want to make from one place to another. So I have full dedicated demonstration and the slides later on about this one. Just hold on for a moment, I will explain everything. Okay, any other question? All right, okay, so let's move on. So optimization, and in particular, I am talking about gradient descent. So gradient descent and gradient ascent, same thing. Ascent is basically the opposite, like you simply go up rather than go down. So same idea you can use. So yeah, okay. So this optimization technique that we are going to talk about is the heart of modern deep learning. Okay, anything that we do in modern deep learning, we are going to use these techniques that I'm going to talk about now in the next few, like today's lecture and maybe tomorrow's lecture. Okay, so those are the things that we do all the time. Okay, and these are all based on the gradient values, the derivatives of the function with respect to the parameters. Okay, so kind of quick review of differential calculus. And essentially, it stands on the high school calculus. You do not need much more sophisticated things than high school calculus for that. Okay, just quick review. Probably most of you know it, but still, quick review. So for a univariate function, if you have to kind of find out this maximum or minimum value, whatever, what you do, that you basically compute the derivative at a particular point and look at the sign of this derivative. So if it is negative, then its function is decreasing. If the positive is increasing, okay, and so on and so forth. And as you can see from the figure, that from the left side, the sign of the derivative will be what? Can somebody respond? What will the sign of the derivative here in this position?
Negative.
It's a negative.
Yes, sir.
Okay, and in this case,
Positive.
Positive.
okay, so basically that will tell which direction you want to move. Okay, depending upon whether you want to maximize or minimize. That's what you do. Okay, and magnitude will tell you how steep the function is, whether it's very steep or flat or something like that. Basically, yeah, that's what. So sign and magnitude of the derivative is a very useful information to figure out that what would be the optimal values, or rather local optimal value of the function and so on. Okay. Now moving to the multivariate functions, because in deep learning or in logistic regression, as you have seen, the number of parameters is basically 1 plus the dimension of this data. So if you have say d-dimensional data, there are d plus 1 parameters in your model in logistic regression. And when you are dealing with deep learning models, you have parameters in millions actually, and sometimes in billions. Okay, so it's essentially multivariate function that you're dealing with. So if you have multivariate function, then you can do partial differentiation with respect to these parameters. So assuming that y is your objective function, so you can compute the partial differentiation of that. So that means keeping all variables constant, you only are changing, or rather considering that only one variable is changing at a time. So you do that. Okay. All right. Now the concept of local and global minima and these objective function that we're going to deal with is called non-convex optimization techniques. So this is an example of non-convex things. The convex thing is like something like this. Okay, this is a convex thing. Okay, there's only one minimum. But in this case, this particular function, the function on the right side, the left side, this function is a non-convex function because you can have multiple like local minima and so on and so forth. And so objective functions that we deal with in deep learning or any other, most of the machine learning cases is basically non-convex function. Smooth function, continuous function, but non-convex function. Okay, and there are additional challenges of non-convex function. If you have convex function, your gradient descent can guarantee the best possible solution. But if it is a non-convex function, then you may get stuck to here. Or if you are lucky, you may find it here, depending upon where you have started off with. Okay. Okay, all right. So now let's look at the actual gradient descent, how it actually works, what we can do, how we figure this out, and so on and so forth. Okay. So goal, what is the goal? That to find the minimum value of a function with respect to the parameters that the function contains. The function has set of parameters and I have to figure out the minimum value. And for what values of these parameters I will have that. So here I have this same old squared loss function or squared error function, which we talked about during linear regression stuff, e is equals to this one and so on and so forth. So you have two possible objectives. You have to find the minimum value of the function, okay, in order to know how well you're actually doing. And second, you need to know the model parameters, the actual values of these parameters, so that you can basically say that I have learned the function, I can use it on the test data. So two things simultaneously you need to know. Okay. But once you know the second, you can basically automatically figure out what you can simply compute that value. All right. Now let's look at the gradient descent, and I think probably this slide will explain the main intuition behind the gradient descent, why you do that. Okay. So what is the role of gradient descent? To find the values of parameters that minimize an objective function. And if it is maximization problem, it is a gradient ascent. Just exact opposite to that. Okay. Now let's look at this function, and this is the function is basically very simple. I'm just to demonstrate you these actual principles of this gradient descent. But in reality, the functions could be complex with many local minima and so on and so forth. Okay. But let's start up with this one. So say we have this function. You can see that there is one theta, parameter theta, or kind of this variable that we have, and we started off from the red region. Okay. Now here is a series of questions that I will be asking you, and you probably will be able to figure out the final expression. Okay. So the first question is, if we start from the red circle, so this is the function that I have, and I have to first initialize this value of theta because I do not know, nobody is going to tell me what would be the value of theta, so I have to randomly initialize somewhere. Okay, that you always have to do, and then you basically go and update depending upon the gradients. So I do not know theta, so I have to randomly initialize this thing. Say we basically initialize this theta value to the red circle at that position point. So if that is the case, then what is the direction of movement from there? You want to minimize this.
Right to left.
Basically that downwards, right?
Downwards.
The downwards. Okay, all right. Okay, all right. That I know that I have to basically move downwards. But how can you get that I have to move downwards? What signal or information you have there to know that?
By taking the slope.
The derivative.
Yeah, exactly. Exactly, right? So basically I can compute the
sign of the derivative.
Yeah, sign of the derivative. Yeah. So by looking at the derivative, basically sign of the derivative. All right. So what is the sign of derivative here, or that red spot?
Positive.
Positive.
It's a positive. Okay. So positive. Okay. All right. So positive. Now then, which direction we should move?
Left.
If it is positive, what is telling you that if you go basically you go up, or rather you basically follow in that direction up, then you are not going to get the minimum value.
Opposite directions.
So opposite direction you have to move.
1 to the power.
So opposite direction you have to move. So basically minus del d f theta d theta. That's the direction basically you have to consider, opposite to that. Okay. Okay. All right. So therefore, how to change the parameters to reach minimum? Because my starting point was red spot, and I know that in which direction I have to move. So I have to update my parameter values. So what would my update equation then? So my update equation would be theta new is equals to theta old. Again, like there is one point that somebody pointed out in the slide in terms of iteration. But anyway, so my new value would be my old value minus r coming to that point to r into f df theta by d theta. So it's actually minus df theta d theta is something that basically telling you which direction you should move. Okay. Now here the question of r. Somebody was asking what is the role of r. This r. So r is called, this is scalar quantity, is positive scalar quantity. Okay, and this is called the rate constant. People call it learning rate, things like that, all kinds of stuff. Okay, so what it is? So it is telling you that, okay, I know from df theta d theta, I know which direction I should move. I have a very precise information about the direction I should move. Okay, but then how much I should move? Okay, how much I should move? Who will tell me that? So of course the magnitude of the derivative will tell me to some extent that whether the function is very steep or very flat, things like that. But then my rate of descent, who will control that? So R is telling you that. R is telling you that, okay, all right, I know my direction very well, but then to what rate, at what rate I should descend. It's a big jump I should make, small jump I should make, and so on and so forth. Because ultimately, you want to quickly figure out your local minima as quickly as possible. So that this R is going to control that jump. In a sense, it is a jump. Okay, so that jump is called the R. So if the value of R is big, as you know, you can quickly descend. There is problem consequences, which you're going to see later in the next slide. But this is the primary role of R. Anybody has any question on this? Okay, all right. So yeah, simple enough. Okay, we see the consequences of different values of R in a moment, but let us look at a small demo in the next slide to understand what is happening. Okay, so the same old picture that I had in the last slide. So I start off with this. So here is my starting position. Okay, now you apply this gradient update rule that you can see on the top. Theta t plus 1 is theta t minus r into d theta. Okay. So if I do the first update, I will be somewhere here. Okay. Second update, I will be somewhere here, and so on and so forth. Now, basically, now if I, for example, accidentally start from the other side of this curve, okay, from here, for example, starting position. Now, in this case, my second update will be somewhere here, because in that case, the sign of this derivative will be positive, sorry, negative. Okay, and so you are going to take the negative of that. So essentially, you are moving towards this. So the after first update, you are going to have here, going to be here. Second update, you are going to be here. Third update is going to be here, and you basically keep on continuing the updates, then you will ultimately reach this particular point, black spot. Black spot, something that your ultimate target. Okay. So any question up to this point from anybody?
Sir, after each update, the magnitude of approaching the goal state will be decreased, right? Because the absolute value of the slope is also decreasing.
Right.
Okay, I was wanting to confirm that only.
Yeah, so of course, yeah, this will come close to that. Yeah, exactly. And then you also have the R. So not only slope, the magnitude of the slope, but at the same time you have also the learning rate R. So you need to adjust R a little bit. We will talk about this the adaptive gradient descent, where you want to adjust these values a little bit, control. There are some consequences of value of R, okay, overshooting and things like that, but you know, we'll look at it.
Sir, R would affect on the number of iterations.
Absolutely, yes. Yes, correct. Absolutely, yes. But R also has bad consequences. Okay, we'll see. Maybe in the next slide, we'll see the bad consequences of that. Okay. All right. So yeah, so if we start from here, let's look at this. So now for multivariate function, what do you do? I'm taking examples from regression. So the same thing that we have, but only difference at the bottom, bottommost like expression, you can see that instead of taking the total derivative, okay, so I am taking the partial derivatives because I have to deal with multivariate function. Okay, so only replacement is that partial derivative, del partial derivative with respect to particular parameter theta I, because I have multiple thetas actually. Okay, that's the only difference. All right. Now, so what is this basic gradient descent algorithm then? If I kind of, as a practical person, if you have to implement this one for your own stuff, what I need to have steps. So what are the steps? So first, initialization. Because I do not know my red spot, nobody told me that. I have to initialize that. So I have to basically randomly set the initial values of these parameters. Okay, so that's called the initialization step, first step. Once we have that, then what you do, repeat until convergence. It's an iterative process. Basically, you are continuously updating your values and so on. That's why repeat until convergence. And get to know the meaning of convergence. In a moment. Okay. So what I do basically, I apply my update equations for all values of all parameters. So theta t plus 1 is theta t minus r into this, the same old equation that I have for all these parameters that I will apply. Okay, so this expression is actually, if you have say 10 thetas in this expression, then this actually there are 10 equations, basically things you'll have to basically apply. I'm just compact way I have written this down. Okay, that's it. So how to check convergence? Two possible ways you can actually do it. Either you can iterate a fixed number of times, that okay, I will basically iterate say 100 times and then I will stop. Okay, or you stop when the parameters do not change much into consecutive iteration. Okay, so for example, some iteration you are here. Okay, at this particular point. And in the next iteration, probably you are here. So if you kind of measure the differences of this parameter values in this two consecutive iteration, you will see the differences are very small actually. So that means you are basically very close to the local minima at least. Okay, so you can also stop based on that. But the general practice, at least in today's like very large deep networks, is that you basically iterate a fixed number of times, because checking convergence is again based on the second condition is very time consuming, because you have sometimes you have billions of parameters. So that takes lots of time. So you basically iterate say 100 times or 200 times and things like this. Okay. So I think I am running out of time. So I will stop here. Tomorrow we will take it further with the other stuff. So if there is any question from anybody.
Sir, is there learning rate parameter in gradient ascent?
Repeat again, please.
Sir, the quantity is small r. Is there in gradient ascent?
Quantity is small r means this quantity is r is basically the learning rate constant. You set it like is a positive constant value that you set. Okay.
So while applying logistic regression, we also check whether the data is having Gaussian distribution or not.
You do not need to check that. There is as such no restriction on logistic regression that it has to be Gaussian.
So, but for better results, we do check it like.
So see, the difficulty is that if you have multivariate data, checking whether this is Gaussian or not, that itself is a very complex task. But no, it doesn't serve any special purpose for that. You just have data, you go and figure out your objective function and simply go and optimize it. That's it.
Excuse me, sir.
Yeah, please.
Sir, R depends on change in slope also, right?
Of course, yes. You are absolutely correct. And that is why maybe tomorrow's lecture you are going to see adaptive gradient descent, where you adapt the value of R with respect to this gradient value and iteration number. You're absolutely right.
Sir. Hello,
yes.
Sir. Sir, can you explain that condensing nearest neighbors algorithm, like that optimization technique used?
Which one?
That where the mismatch classification mismatch happened and we added some to that.
Actually, your voice is breaking too much, so I cannot
Sir,
hear.
I'll type in the chat.
Chat, okay, all right. Let me just check the chat.
So,
condensing nearest neighbor. Yeah, okay. Yeah, what's your question? Classification mismatch. Okay. Okay. Should I explain that again?
Yes, sir.
Okay. So I can do one thing. It is all. I'm running out of time. So can you tell me your name? Maybe we can catch up sometime today, sometime at your convenience. You just let me know when you are ready. I can just explain to you one. Is that good for you?
Yes, sir. After 1 o'clock, like.
Yeah, sure. You just drop me an email whenever you are available. I am available in the afternoon. We can take a short call through either the MS Team or Google Meet, or I can try to explain to you. Okay, no problem at all. Yeah.
Sir, your email ID.
My email ID. Oh, my email ID is jia.paik@gmail.com. First three character of my first name dot my surname @gmail.com.
excuse me, sir.
Okay, please.
So this gradient descent is based on the instantaneous derivative, right? Like we cannot, if the derivative at some point is telling us to move in one direction, but if we have many local minimas, and later on that is not the global minimum.
Yeah.
So we cannot like predict what will happen afterwards, right?
No, you cannot predict that. There is no way to know that.
Okay, sir.
That's a very difficult. That's why it is a very difficult problem. I mean, it's.
Okay, sir.
Yeah.
Thank
So
you, sir.
one possible practical solution, and not solution, practical way of dealing with that, to some extent, is that you run multiple times with multiple initial points, because the whether you get stuck to a good minima or bad minima depends on where you started off with, right?
Yes,
your
sir.
initialization. So what you do, you basically run multiple times with different initialization, and then check your objective function value, and from that probably you can guess what is good, what is bad.
Okay, sir.
Okay.
Sir, how do we fix the number of iteration? Do we set any accuracy?
Well, I think I do not know any good recommendation for that. You just like look at maybe you can look at the loss value, okay, or like accuracy values, okay, because after every iteration you are computing your accuracy values as well. So probably when you see that accuracy value is high, you basically stop.
Okay, sir.
Okay. Okay, so all right. Thank you very much for attending, and we'll see you tomorrow morning.
Thank you, sir.
Thank you, sir.
Thank you. Bye bye.
Thank you, sir.